Okay, so thanks a lot for this invitation. I'm going to talk about, the title of my talk is going to be Cosmological Selection of a Small Weak Scale from a Large Vacuum Energy and Minimal Approach. So this is work done in collaboration with Dibbo Chattopadhyay and Sushoman Chattopadhyay, and the preprint is already out, so you can check if you want. So most of the work was done by these two students. So Sushoman is here, and Dibbo is also a PhD student at TIFR. So as you can guess from the title, this is a new. This work is tries to address the hierarchy problem. So of course, most of you know about the hierarchy problem. So I'll give a very quick introduction. So the hierarchy problem arises if you try to write the Higgs mass, the physical Higgs mass. So here I've written in terms of mu h squared, but once you know mu h, you know also the Higgs mass. So if you try to write the physical Higgs mass in terms of the parameters of a UV theory. So let's say at some high scale, so high energy scale is like small length scale. So small length scales are always more fundamental. We always try to describe macroscopic things in terms of microscopic things. So so small length scale. So suppose you have suppose you have this term, this h dagger h term, and the mu, and you have a way to calculate. So one of the assumptions that is going into this is that there is some theory which tells you in terms of the parameters of that theory. So this alpha I UV is some UV theory with its own parameters. So in terms of the parameters of that theory, you know this should be mu h. So there are two mu's here. One is the renormalization scale, that is just mu, and this is mu h. So this should have been mu h. So let's say mu h is calculable in this theory. So in terms of the UV parameters, you know what mu h is, and then you run down, and these green lines are like threshold corrections. So whenever you see a green line, as you run down from high energies to low energy, there is some new particle that's coupling to the Higgs, and as soon as that happens, you get a new loop correction. So for example, here maybe there's some particle at the Planck scale, there's something at Guth scale, then there's something at TeV scale. So in the end, when you will predict the Higgs mass, you'll pick up all these contributions, and you'll get an expression like this. Now, as you well know, that if these masses are very big, for example, if there's an order Planck square correction, there might be an order maybe you have some new physics at Guth scale, or maybe you have some new physics at the TeV scale. So these numbers are pretty big. Even if it is at TeV scale, it's pretty big, whereas the left hand side is just about 10 to the 4 GeV squared. So what this means is that to get this small number from these big numbers, you need to, so this small number can be obtained only in a very small fraction of the UV parameter space. So if you want to write, so only a very small region of the UV parameter space will be consistent with a light Higgs. Now, of course, you might solve the hierarchy problem up to a certain scale, but even then you should, so even if let's say above 10 TeV you solve the hierarchy problem, but even then this 1 TeV squared number is starting to get big. So that is in short what the hierarchy problem is when you're trying to write the Higgs mass in terms of some UV parameters. And of course, we know that the most of the solutions to the hierarchy problem used some symmetry. So there were these so-called symmetry-based approaches. So in these approaches, you embed the standard model in some other framework, in some more elaborate framework where there is some symmetry which prohibits the Higgs mass. So in other words, if mh becomes 0, or if this mu h becomes 0, that is that enhances the symmetry. So the mh is protected by symmetry, and a corollary of this is of course that whatever is breaking this symmetry, because there is no such symmetry in the standard model that can protect the Higgs mass. So whatever is breaking this symmetry, for example, if it's SUSY, it's the soft SUSY masses. If it's if the Higgs is like Goldstone, if it's a shift symmetry, then there is some. So whatever is breaking that symmetry, the Higgs mass should be of that order. Now that would predict that you should see new particles around the Higgs mass, but we haven't seen any such new particles. So this is very briefly the argument why people used to believe that the Higgs mass, the fact that the Higgs mass is around a few hundred GeVs, that should predict other particles close to the LHC as Kajari also mentioned in her talk, that people expected not just to see the Higgs but other states that have unfortunately not been seen so far. So the LHC null results are telling us that we have seen so far no such states. Of course, this might change. So as Kajari was saying, maybe in the next decade we will see some new particles, but already we are a decade since the discovery of the Higgs boson. So we can at least think about this question: what if the LHC doesn't see any new physics also in the future? So was this argument wrong? What was wrong? So my philosophy is that maybe it was wrong, and of course it would be wrong if you don't see anything new. It would be wrong, but maybe it points, but maybe it's wrong in an interesting way. So what that means is that one of the assumptions that went into this argument must be wrong, and then you can try to think what was the loophole in the argument. So I found this quote, and so Niels Bohr said that the opposite of a fact is a falsehood, but the opposite of one profound truth may well be another profound truth. So maybe the hierarchy problem argument was wrong, but because it's not easy to find a loophole. I mean, of course, there are various assumptions, and there are well-known ways now people know how to maybe get around this. But each of these different ways, there are not so many different ways of getting or finding a loophole. So in some sense, if you want to solve the hierarchy problem today and you don't want to have any new physics at the TeV scale, it's a more constrained thing. It's not like anything goes. It's only maybe there are a few ways of getting around it, and that's why maybe it's interesting theoretically, because there aren't. So in some sense, before the LHC null results, you could write hundreds of models, but now maybe it's much more constrained to write a model that is, in fact, as you will see, it is quite difficult to write a model that can accommodate a light Higgs and no new physics at the LHC. So there are various new approaches. So there are some approaches which says, okay, maybe there are no new physics till the Planck scale, and somehow gravity also doesn't give any new corrections. So one of the approach that I will talk about today is this cosmological selection approach. And one way to introduce it is to say that we were saying, so in the beginning, the first slide I showed, I said, okay, so if you know if you try to predict the Higgs mass in terms of the UV, then there are then you run into this problem that the UV parameter space must be very you have to fine tune in the UV parameter space to get a light Higgs. But one possibility is, of course, that there is no one-to-one relationship between the Higgs mass in the IR and the UV in the UV theory. So what if the fundamental theory has many ground states, so many phases, and this can easily happen, right? You have many scalars in the UV, the scalars get waved. Let's say these scalars couple to h dagger h, and so phi I h dagger h. So in different vacuum states, you will have different Higgs masses. So maybe instead of there being a one-to-one relationship, you have different Higgs masses. And of course, it's well known that this happens in string theory, but you can also easily do it in a field theoretic setup. Just have many scalars and all of them coupled to h dagger h, and this, let's say you have n scalars, they have some complicated potential, and in general they have 2 to the n or e to the n vacua if you try to minimize, and in each of these vacua the Higgs mass may be different. So this is a logical possibility that we must think about. So this is what I would mean by a landscape, that in the IR there are many ground states, many different vacua where in each the Higgs mass is different. Okay, so now so in the next few slides I'm going to review. So there have been solutions that have been proposed, as you will see, in the last decade, which use this kind of an idea. So let's say there are many vacua, and again, because of this, because of what we saw in the first slide, most of these vacuas will indeed have the Higgs mu squared very high, like m Planck square or m Guth square or whatever. But in some very small number, just by accident, you might have a Higgs mass square that is small. So maybe here I have written 2, but maybe this will be 2 out of billions, where the Higgs mass just accidentally will be small. So if you scan over all possible vacua, and you have many of these vacua, so just by chance, some will have a small Higgs mass. And now if you have a mechanism to select these small ones, then you can find an explanation for the lightness of the Higgs. Now, one mechanism that is known, but this was proposed in this paper, is the anthropic selection. So it turns out that if the Higgs wave was too large, then proton or neutron won't be stable. You can see the details because basically the contribution of the up and down mass, the bare masses, the up and down mass, because as you know, the proton is mostly the mass is coming from QCD, but if the wave is high, then mu, md start contributing, and the neutron-proton mass difference changes, and then you can have all kinds of things. But of course, this kind of assumes that you are keeping the Yukawas fixed and changing the wave. But so basically, the anthropic argument selects some range of mu and md, not the electroweak wave, because you can imagine that the Yukawas are also changing in your landscape, and then you can't say much. So this is maybe one flaw of this argument. So you have to find a reason why the Yukawas don't change so much, and if only the waves change, then you can say, okay, only in some of these regions of this landscape are consistent with there being life. So since we have observed, we know there's a life, that's an observation, and that constraints that tells you. So this is one approach, but there have been recently many approaches where you find a non-anthropic selection mechanism. So you have this landscape, and then you find some non-anthropic mechanism, and typically these things add some scalars, and the dynamics of the scalar is such that only some of these vacua get selected. And the good thing is that unlike anthropic models, there are clear signatures. You can see the scalar, there's weak scale physics and so on. And again, there are not so many. So one of the first papers was this Relaxion paper, where it wasn't like they even needed a landscape. So they had some slowly rolling field which could in time scan all these different vacua, and then once you get close to this 100 GeV scale, it stops. And why? So these are some of the papers, and most of them are from the last decade, as you see, which try to find this kind of an explanation. And so our work is a continuation of this approach. And so there is some principle that almost all of them are using, and the principle is that now the mu squared, as I said, that earlier approaches, symmetry-based approaches, used to say that mu squared going to 0 is special because you recover some symmetry. But in these models, mu squared equal to 0 is not special because it recovers some asymmetry. Indeed, as you saw, symmetry-based solutions are hard to accommodate. It's hard to accommodate them with LHC null results. Mu squared equal to 0 is special because it separates two phases. So another way of phrasing the hierarchy problem is that the mu squared of the Higgs is very close to the point which separates the two phases, the electroweak symmetry breaking and preserving phases. So maybe something happens near this critical point that so basically what happens is the Higgs wave plays some dynamical role and is so you will see. So basically there is some light scalar that couples the Higgs wave, and whether or not the Higgs has a wave plays a decisive role in the dynamics of the scalar. So this is like, if I have to really summarize it very quickly, what these models do. Yeah. So already there is one physical quantity which behaves in a very special way near mu squared equal to 0 already in the standard model, and that is the vacuum energy of the Higgs. By the vacuum energy of the Higgs, I just mean the value of VH at the minima. So if I have mu squared equal to 0, I know that the Higgs gets stabilized at the origin. Now as I keep lowering mu squared, so this is a lower value of mu squared, the orange, and then I keep lowering it, I go to the green, what I see is that the vacuum energy is decreasing. So vacuum energy is decreased. So now if I plot this, I'll get, if I plot this, I get something like this. So if mu squared is positive, the Higgs vacuum energy doesn't change at all. It's constant, it's at 0 classically. And then when mu squared starts decreasing, if you go back, the Higgs vacuum becomes deeper and deeper. So that tells me that the Higgs vacuum energy does something special around mu squared. So once it gets a wave, the Higgs vacuum energy behaves in a very different way. It keeps going down monotonically. So this suggests a selection mechanism. And so how can we use the fact, what does the vacuum energy couple to? Of course, gravity. So what can happen is during inflation, and this was actually in a different kind of a model. It was suggested first in this paper and also used in these other papers. What can happen is that if the Higgs vacuum, so during inflation you have different causally disconnected patches, and very naturally these patches can sample different vacua. So because there are quantum fluctuations, so you don't have to do anything extra. If you have inflation, then different patches, the scalar field values are different. In general, they can be in different vacua. And then you can see that the effective parameters in each of these patches are different, and in one, if the vacuum energy is much bigger than the other because of, as you know, exponential expansion, in a very short time this kind of patch will dominate everything. So this kind of mechanism was used here, but in a very different setup that maybe I'll briefly mention. So we borrow this idea from these papers, but we try to construct a very simple example of a model. So in other words, large Higgs waves are disfavored over small Higgs waves. So small negative Higgs masses would be, so if you just had standard model, let's say, and there was some mechanism or some way of having different mu squared in each patch, then automatically you see that the very big large negative mu squareds won't expand much. Only the positive mu squareds or the small negative mu squareds will, because very big, very negative mu squareds will mean large wave and very deep Higgs minima, so they will have smaller vacuum. Of course, I'm assuming all kinds of things. Vacuum energy won't just come from Higgs, it won't come from other places also. But very naively, you can make a model like this. Sorry. So you see here, so as I said, I had all these different bubbles which are like these different patches. So I can already, just at the level of standard model, if maybe I can make a model where you can exclude very large negative mu squared values just because the vacuum energy is so low in that. But the issue is that any positive value of mu squared will still get selected, because then you are, in fact, any positive mu squared, the vacuum energy, there's a plateau. The vacuum energy is the same and at its maximal value for any positive mu squared. So these will get selected. Okay. So what we did, motivated by this, so you can just do a simple model where VH, which is the Higgs potential, as I said, large wave implies low vacuum energy, so large waves would be, or large negative mu squared values will be excluded. But then we add a scalar phi such that this term, which is sometimes in this literature called the trigger term, the scalar phi potential will depend on the Higgs wave in such a way that if the Higgs gets wave, this term will give a negative contribution. So let me show you a simple example. For example, if you have a scalar which has, if the Higgs wave is 0, let's say it has a Mexican hat potential. And then as soon as the Higgs gets a wave, you go from this to this and you raise the vacuum energy of this scalar. Okay, I should be done well. So you raise the vacuum energy if the Higgs gets a wave. Okay. Now of course you don't raise it beyond a certain value. You just sit here after some threshold, after this kappa h squared is equal to m squared, you don't raise. Now in patches where the Higgs wave is much bigger, you don't raise it any further, but then the Higgs part of the potential starts getting more and more negative. So in the overall, your vacuum energy will peak at a small Higgs wave, not for a Higgs wave 0, but at a small but finite Higgs wave. The problem with this model, however, would be that if you write this term, then you should also write a term. So because we want a very high scale of new physics, you can just close the Higgs loop and you could have written this term already. And this is kind of quite a common problem in these kind of models. Although I should say that if you look at these models, they're completely different. This model is completely different from the other models, but there are some universal features, surprise, because all of these models have some field phi and then they have to couple it to the Higgs. So if you couple it like this, so whatever this h dagger h wave will do, this term will already do that, right? Unless lambda is less than 4 pi v. So unless you have some new physics that cuts off this loop, so you're back to the same problem. Unless lambda is less than 4 pi v, you could already have had a term that did this for you, and so this kind of a term is problematic because of that reason. And this is, as I said, quite a general issue. In fact, this was argued in this paper that it's quite a generic issue, that whatever can be triggered by h dagger h can also be triggered by closing the loop. So this is, and because of this, so you have to do something more. So either you have to cut off this loop, have some new dynamics that at the TV scale below this 4 pi v, or the other option is to go to a 2 Higgs doublet model, which is the more neater option. So instead of having 1 Higgs, you have 2 Higgs doublets, and then now the term looks something like this. Now you can't close the loop. So now this term looks like this, and you can show that you don't have a big enough. So at the loop level, you can't generate a term that is phi squared times something order electroweak wave. So that is guaranteed by having this, and then there's some symmetry Z2. You can show that even at 2 loop level, you don't generate a dangerous contribution and so on. And so basically we have some kind of light scalar phi. So now let me, because this was just kind of motivation, but now the actual model I can go through very quickly because of all this big background that I've given. So this phi has something like a pseudo-Nambu-Goldstone boson potential. So it is a much lighter. So the mass of phi is much lighter than F, and you can generate this in many different ways. This is a generic sort of PNGV potential, and then you have a 2HDM, which is again a very generic kind of 2HDM with this kind of discrete symmetry, and you have a term which breaks both the shift symmetry of the phi and Z2, and we have checked that everything is kind of so for example, this breaking should not be too big, this should not induce a term bigger than this mu square, and all that. We analyze all these constraints, and then what we want to do is, now we want to maximize the vacuum energy of this potential, and hopefully it will be maximized at a small Higgs wave which is much smaller than the cutoff. Now so let's say now I go to the cosmological picture where we have many kind of vacua. In each vacua the parameters of my low energy theory are different. In particular, the parameters of this 2HDM, these lambdas and mu's are different. So for example, this alpha HI tells me the parameters of the 2HDM sector, and they are different in different vacua. Then there is some inflaton contribution because I am doing inflation, so I must have this term. There is some CC contribution. Now now you can show quite generically that it's done in papers much before related to inflation and internal inflation, that during inflation it's quite generic that if you have many vacua, that you go to the highest vacuum energy state, as we were saying, and this has been done quite rigorously in many papers, and it's also reviewed in our work. So it's quite generic. You will go to the highest energy state, and we'll assume that highest energy state will have each of these terms maximized. So you could have asked me, why are you just looking at the Higgs contribution? You have a CC, you have other things that can contribute to the vacuum energy, but it turns out all of these must be independently maximized, including the Higgs contribution. So with that, so that tells us that it is it makes sense to maximize this individually. And then we need another assumption, because you see during inflation it's not like every field is at its minima. The fields can, there's some quantum spreading, so the fields can deviate from their minima. So so these are, so you have this so-called probability you have these probability distributions. They are not exactly like probabilities, but which you have to solve this Fokker-Planck equation to get them, and so on. And you can show that under certain conditions the fields do peak at their minima if the Hubble scale, if you satisfy these constraints. Basically the Hubble scale has to be much less than the weak scale, and so on. Under these conditions you can show that even during inflation all the fields will be at their minima. So otherwise the whole exercise doesn't make sense. Now if that happens, because the Hubble scale is less than V and our cutoff will be order the vacuum energy during inflation, that gives a bound on our cutoff which is 10 to the 10 GeV. So this unfortunately tells us, because the Hubble scale cannot be bigger than V, that our theory has a cutoff of 10 to the 10 GeV. Now, so now most of the main part of the work in this paper was to look at this 2HDM potential, phi plus 2HDM, minimize it, find the vacuum energy, and then vary the parameters to find where the vacuum energy peaks. So we can do this in two steps. We can first what we did is we varied mu1 squared and mu2 squared. Varying mu1 and mu2 squared is kind of like varying V1 and V2, like the minimization conditions. You can trade mu1 and mu2 for V1 and V2, the wave of the two Higgs doublets, and that is like varying V and tan beta basically. So we vary V and tan beta to maximize this this whole potential. And then in the next step we will vary the quartics and try to maximize the potential with respect to that variation. So first, just the variation of mu1 and mu2 square. As I said, the very simple picture that I said at the beginning actually holds under some, there are various subtleties that I will discuss a bit. So if the Higgs wave is 0, as you know, the Higgs potential is like this, but the phi potential to start with was like this. Now as I increase the Higgs wave, at some point the phi potential flips from this to this form, but the Higgs potential becomes a bit more, it dips a bit. And then once I keep increasing the Higgs wave, the Higgs mu squared in vacua where the Higgs mu squared is very large, the phi is settled here, but the Higgs potential becomes deeper and deeper. So now if you look at the vacuum energy, it is maximized in this middle panel. So the vacuum energy is maximized for a Higgs wave which is 100 GeV, And indeed, this is much smaller than the cutoff, which is like 10 to the 10 GeV for us. And so this is once you vary mu1 and mu1 squared and mu2 squared. Now, what is interesting is, and this is what we spent a lot of time doing actually, is that, so I'm saying there are various vacuum, and let's imagine for the moment that the only thing different between the different patches is that the value of mu1 squared and mu2 squared is different. And now I try to maximize this term, this Higgs contribution to the vacuum energy, and then it's an exercise, like basically a minimizing thing.
So this 100 GeV emerges.
No, 100 is order 100.
Yeah, I understand. I mean, it is 10 to the 2, 3, whatever it is.
Yeah, it's much smaller than the cutoff. That's the.
It's and your cutoff, the 10 to the 10 GeV.
Yeah,
and that you got from.
So I will show you. Let me show you the expression. So it emerges because. It emerges because, as you see, once the Higgs wave, if the Higgs wave is 0, this is at the potentials of both the things are fixed completely. Okay, this is a fixed Mexican hat potential, and your total vacuum energy is this negative value. Once I start increasing the Higgs wave at a specific value, that of course doesn't need to be 100 GeV, but there's no reason for this value to be of the order of cutoff. It's basically this value comes from here. Basically, I want to. Basically you see here that this PNGB has a negative mass squared, right? And this Higgs wave is making that positive. So if I make the Higgs wave large enough, the mass squared here will flip the sign, okay? And the value where that flips has nothing to do with the cutoff. Because this mu wave, this is a technically natural thing that can be much smaller than the cutoff.
No, I'm just wondering, I mean, without any other reference point, you are getting some number which is of the ballpark of weak scale. I mean,
no, that's true. So that maybe I should have that's not so basically what we'll get is it's maximized at this thing. So at this value mu phi f, which can be weak scale, which can be electron volts, anything. But then you have to choose your mu phi and f to give you the observed weak scale. So this could have been anything. This could have been
right.
But the whole point is this can be much smaller than the cutoff. Now what it actually is depends on the observation that the weak scale is 100 GeV. So mu phi f must be equal to 100 GeV, but it could have been 1 electron volt also, basically anything. Like these are free parameters in my theory. So I will fix them to get 100 GeV.
The corrections to mu phi f due to loop corrections, that is under control, or can
because because this is like the parameter that breaks the shift symmetry. So it's completely correction is multiplicatively corrections to mu phi f, mu phi are of order mu phi. So mu phi I can discuss, but it's you can show that that potential will get mu phi will get corrections that are multiplicative. Okay, so this picture which holds I mean, this is a very simplistic picture, but there are various subtleties. This will hold only, it turns out, if the quartic satisfies certain conditions. So for example, there are much more complicated, once you do the minimization, you could have had that both the phi and the Higgs gets a wave and things like that. But that, to prohibit all those kind of things happening that can kind of spoil this picture, you need various conditions on the quartics. And this might have been, I mean, we do this in 2H DIMMs all the time, that the quartics have certain conditions. And of course, like for example, if there are other phenomenological things, for example, if this is not true, the photon can get mass and so on. But the nice feature of our model is that all these conditions we found on the quartics, once we were varying mu h squared, the two mu squares, they can automatically get selected in the second step. So when you vary the quartics, it turns out that if you respect these conditions, only then the vacuum energy is maximized. So first we were maximizing vacuum energy with respect to the variation of the mu squared. But if you do it with respect to the variation of the quartics, it turns out that you will automatically select this region. So we don't have to impose any of these conditions. They naturally are okay. I'm just two more few. Okay, so that is basically the thing. And then in the end, what happens is that in the beginning you can have patches with all kinds of electroweak wave, but the ones which are this maximal energy ones expand and occupy most of the volume. So that's the essence of our mechanism. So very quickly, the one thing I wanted to say is that to connect to some experimental facts is that this condition, so when, as I said, I was maximizing with respect to V1 and V2. So that gave me some condition where it is maximized with respect to the V and also tan beta, because V1 and V2, there are two parameters. So our model gives a prediction for what tan beta is, and that it can be experimentally verified. So this condition that the vacuum energy is maximized at this place can be turned into this equation which connects alpha, beta. All of these are observable things, as you know, people who are familiar with 2HDM phenomenology. Some like beta can be measured by charged Higgs and pseudoscalar decays. Alpha is related to the CP even Higgs couplings and so on. So all these things can be measured. Okay, so this is a slide where we show we can predict basically the value of cos alpha beta for a given value of the heavy CP even Higgs and tan beta, and this is of course can be measured in if you may measure couplings of the CP even of the standard model like Higgs coupling deviations, you can measure this thing and we can predict it. So in terms of two other measurable parameters, we predict a third, so which is a nice feature of this. And of course the phi itself has its own phenomenology, and it can be dark matter in some region, and there can be bounds from equivalence principle violation, and those have been shown here. So this is very quickly to say that there are very clear phenomenological signatures, and I will just skip this part. So there are previous works that do this, but the main difference is that they try to have a mechanism for scanning the Higgs mass, and for that then they require very complicated kind of potentials. The other papers I was showing you. So basically they require something like the relaxion potential, where you have a periodic term, or and these are very contrived. So this can be motivated if you have something like a clockwork mechanism, and the clockwork is, as you know, many scalars with a very specific potential. So in some sense it's very contrived to get these kind of potentials, and so all these models have this potential, these three models. And because we are doing something more minimal, we don't want a mechanism that scans the mu squared in different vacua, we just use the phi for selection, we don't encounter this problem. And there are many nice features. For example, in those models have some crazy things always in those models. For example, the field value of phi is trans-Planckian or above the F, or the number of E-folds is very, very large, but in our model is much simpler and also doesn't have these issues. So I'll let you read the conclusion. Thank you.